Hello, in this video I will be talking about another aspect of acids and bases, that is specifically the concept of pK or pKa, sometimes known as the acidity constant or the acid dissociation constant. It's a property of a specific acid. Okay, so what is the pKa? Well, it's a shorthand way of specifying the strength of a specific acid. Now that's very important. It's not the acidity of a specific solution. Again, that's pH. pH is the measure of how acidic a solution is. Solution, in other words, it's got water and some acids and or bases dissolved in it, and there's a certain amount of H3O plus in that solution. That's what the pH specifies. pK is a specific property not of a solution, but of an acid that you put into solution, possibly. So for example, this compound is called mandelic acid. It's just a specific acid that I pulled out of the stockroom. There are lots of different acids in our stockroom, and there are thousands and hundreds of thousands of different acids that have a pKa value. Each one has a different pKa value. So the pKa of mandelic acid, I happen to know because I looked it up. The pKa of mandelic acid is 3.85. Right on the label, it could say pKa equals 3.85 for this particular acid. It doesn't because pKa's generally aren't listed on labels of acids. Believe me, I looked and I couldn't find any, but it could be. It's just a property of a specific acid. This particular compound has a melting point listed. The melting point is listed as 119 to 121 degrees centigrade. Again, that's just a property of this particular compound. pKa is also a property of this particular compound. So what is it? Well, let's analyze the parts of this little symbol here. The Ka is just the equilibrium constant for this particular equilibrium right here, and I'll talk about that in just a minute. The P, the little p in front, means the same thing as the little p in front. pH means it's basically just the exponent on the Ka, or the log of the Ka number. Again, Ka is a number, just like any other number, and like any number, you can take the log of it. So the pKa is the log of the Ka. Actually, it's the negative of the log of it. The little p in front doesn't just stand for power, it stands for negative power. So for example, if a compound had a Ka of 1,000, that would be 10 to the third. The pKa of that would be negative 3, because you take the negative of whatever the exponent is, and that's what a log is. So pKa is the negative of the log of the Ka. It's just a way of writing it in a different format. So the Ka that we're referring to is the equilibrium constant for this particular reaction. Now I've used Ha as a symbol for some acid. This is the base that that acid is going to react with. Now specifically it's water. Any other base could be used with any acid, so this acid could react with any base, but in order to define the Ka, we have to use water. It's just the standard that everybody has agreed we're going to use. So we put the acid in the presence of water. This equilibrium happens. As with any acid in water, you always get H3O plus, and then you get the conjugate base of this acid, which is A minus. In other words, the HA has just given away an H plus to become A minus, and the water picks up that H plus and becomes H3O plus. So again, this is just a generic equation for any acid plus water, but because it's an equilibrium, it has an equilibrium constant, and we learned how to write equilibrium constants. By the way, the A means acidity, so it's a specific kind of equilibrium constant for this specific reaction. And like any equilibrium constant, it's the concentration of the products, so the concentration of H3O plus times the concentration of A minus, that is whatever the conjugate base of the acid is, and then divided by the concentration of HA, some of which will remain in solution because this is a weak acid, so it doesn't completely ionize. Some of it remains in HA form. Notice that we don't put the water into the equilibrium constant because, like with all equilibrium constants, we don't put in liquids, and that's the solvent, so it's a liquid. And this just reminds us that HA is the specific acid, and the standard base that we use is always water. Okay. So in other words, if we wanted to measure the Ka of mandelic acid, which by the way we don't have to because we just looked it up, but if we wanted to measure it, we could put some of this into water, measure how much H3O plus there is, how much A minus there is, how much HA there is in the solution once it's come to equilibrium, and then put those numbers into this formula, and that would give us the Ka. Then to get the pKa, we would take a negative of the log of that number. So again, just to be clear, the Ka, or the pKa for that matter, is the property of a compound, not the property of a solution. Like I said, we can look up the pKa or the Ka. So let's do that now. I have a table that I downloaded. So for the acid called 2,5-dimethylpyridine, the pKa is 6.40. Let's go all the way down here to mandelic acid. Again, that's what this acid is. And notice that it has a pKa of 3.85. Again, all I'm doing here is emphasizing the fact that a specific acid will have a specific pKa. It doesn't have anything to do with the acidity of the solution that it might or might not be in. In this case, it's not in solution, it's a solid. So to this point, we talked about the definition of the pKa and the fact that it's a constant for a particular acid. Like, for example, mandelic acid, we saw had a pKa of 3.85. Let's just do a few more examples and nail down the mathematics involved with it. So we can look up the pKa of acetic acid. Now, acetic acid is the acid that's in vinegar. Vinegar is only about 5% acetic acid. The other 95% is water. But the acid itself is acetic acid. So here is the structure of acetic acid, and it's this hydrogen that is acidic. Remember, our definition of pKa depends upon an equilibrium constant when you put the acid, so acetic acid, into specifically water. So when acetic acid reacts with water, it produces H3O+, as all acids do when you put them into water, plus the conjugate base of the acetic acid, which is the same as acetic acid, but with the H plus taken off, so it's got a negative on that oxygen. And then, since this is an equilibrium, the equilibrium constant is defined as the concentration of H3O+ times the concentration of the conjugate base divided by the concentration of the original acid that's in the solution. And since it's an equilibrium, there is some of the conjugate base and some of the original acid in the solution. And it turns out that when you put acetic acid into water and you measure these three substances, it will come out to be 1.74 times 10 to the minus fifth. That is the same as 1 times 10 to the minus 4.76, and therefore the pKa is 4.76. Another example, NH4 positive is an acid, so it has a pKa. Turns out that the pKa is 9.24, so the K value for the corresponding equation, again, acid plus water to give conjugate base plus H3O+, that's an equilibrium. The equilibrium constant is defined as the concentration of H3O+ times the concentration of ammonia divided by the concentration of ammonium. Again, ammonium being the original acid that you put into water. That equilibrium constant turns out to be 5.75 times 10 to the minus 10th, which is the same thing as 1 times 10 to the negative 9.24. And so therefore its pKa is 9.24. So you should be able to take a pKa value if you're given that, turn it into an equilibrium constant, then if it happens to not have a whole number for its exponent, if you want to convert it into a number with a whole number on your calculator, you simply put in 10 to the negative 9.24 power, however your calculator works to do that, and you will find that it's 5.75 times 10 to the minus 10th. That's the equilibrium constant for the reaction when the acid is dissolved in water. Or vice versa, if you're given that Ka value, you could convert it into an equilibrium constant. If you're not sure how to do that, let me know and I'll help you out with that. So Ka and pKa allows us to compare how strong an acid is. For example, how much does it want to give away H+? That's what we mean by the strength of an acid. The stronger the acid, the more it wants to give away H+, so the bigger the Ka value would be, and the smaller the pKa value would be. So let's compare the previous two acids, which is stronger. We saw that for acetic acid, the pKa was 4.76. For ammonium ion, the pKa was 9.24, which is a stronger acid, ammonium or acetic acid. And the answer is the smaller pKa value is the one that corresponds to the stronger acid. So acetic acid would be the stronger acid. Its pKa is only 4.76 as opposed to ammonium, which has a pKa of 9.24. That's a pretty big number as pKa's go, and therefore we know that ammonium is a pretty weak acid. Again, the bigger the pKa, the weaker the acid. Why is it that the bigger number is a weaker acid? Seems backwards. Well, here's the reason. Because if the pKa is 4.76, the Ka is 1.74 times 10 to the minus fifth power. Notice that 4.76 is about 5, so the pKa will be something times 10 to the minus fifth, and pKa of 9.24 means the Ka is only 5.75 times 10 to the minus 10th power. That's a way smaller number, therefore the Ka is a smaller ratio. Therefore, the acid is a weaker acid because it wants to go over to the right-hand side less than does acetic acid. Again, notice they both highly favor the left-hand side. Those are both 1.74 times 10 minus fifth and 5.75 times 10 minus 10th are both very small numbers, so these are very weak acids, mostly favoring the left-hand side. But of the two, acetic acid tends to go to the right-hand side more than ammonium ion tends to go to the right-hand side. So you can compare the Ka or the pKa to compare acid strengths. So just for a quick quiz, which is a stronger acid? Benzoic acid with a pKa of 4.19 or phenol with a pKa of 9.95. And if the pKa is 4.19, the Ka is 1 times 10 to the minus 4.19. If the pKa is 9.95, the Ka is 1 times 10 to the minus 9.95. That's a smaller number, and therefore a weaker acid. So the stronger acid is the benzoic acid, which we would have predicted anyway based on the simple rule that the smaller the pKa, the stronger the acid. That finishes that lecture. Thank you very much.